All right, so we're continuing our discussion of section 11 for the binomial theorem. We finished the first half of the notes. Now today we'll start talking about the rest of it, the second half. So just kind of as a reminder, we're going to go through some of these things. I know it's maybe been a while since we've looked at some of this. Remember the binomial coefficient, it's another way of getting this leading number in front of each term. On the first side of these notes, we use the Pascal's triangle, but we also have used this formula to calculate each one of those. So we could certainly go look at the first at the first value in the fifth row, the Pascal's triangle, or we can think of this as a combination of 5 choose 0, we call it. The next one will be 5 choose 1. This is a combination of 5 choose 2. And so on, 5 choose 3, 5 choose 4, and 5 choose 5, following the same pattern here. Okay, so how do we calculate that? Remember we did some examples here. So a combination of 10 choose 3 is 10 factorial over 3 factorial, and then the difference of the two numbers, 10 minus 3, is 7 factorial. And then we simplify that, and in this case we got 120. Okay, so just to go through a couple of things to remind us about when we expand binomials to the nth power. We know that there's going to be one more than that terms, right? So if we raise something up here, for example, we raise this to the 5th power, we had 6 terms. So if we raise it to the generic n power, we will have n plus 1 terms. Remember too that the first term always has a leading coefficient of 1 to start with, and it's x to the n. The last term is simply y to the n. All right. Remember too that the exponent on the x values are always decreasing by 1 as we go across. So, they're decreasing 5, 4, 3, 2, 1. The y, or the second value in the binomial, its exponents are increasing by 1. So if we look, we see 0 to the y to the 0, y to the 1, y to the 2, and so on. Okay. Also remember that the sum of the exponents on each term is always going to be equal to n, in this case up here 5. So 5 plus 0, 4 plus 1, 3 plus 2, 2 plus 3, and so on. Those all add up to 5. And then there's symmetry in the coefficients. So for example, if we look back up in this one, 5 to the 0 will be the same as 5, not 5 to the 0, sorry. A combination of 5 choose 0 is the same as a combination of 5 choose 5. A combination of 5 choose 1 is the same as a combination of 5 choose 4, and so on. 5 choose 3 will be the same as 5 choose 2. So they're both 1, they're both 5, they're both 10. So that's what this last thing to remember, number 5, is saying that a combination of n choose r is the same as the combination of n choose n minus r. So 5 choose 1 is the same as 5 choose 4. Okay, so now let's use this whole idea of that binomial theorem. Let's get to the new stuff that we're going to talk about today. And we're talking about the actual binomial theorem. What we were talking about before was using some of the components of the binomial theorem, but here we're going to use the actual binomial theorem. So, so notice if I take a binomial raised to the nth power, I could write out that expansion. So the first term is going to be the coefficient can be found. Again, we could go to Pascal's triangle, but here we have the binomial theorem allows us to say, well, that's just going to be a combination of n choose 0 times x to the n. And then the next term is going to be, as its coefficient, a combination of n choose 1, and then x raised to the n minus 1, so 1 less, right? It's decreasing by 1 every time, and also y is increasing by 1. Here we had y to the 0, we left it off. Here's y to the 1. The next term is going to be a combination of n choose 2, and then it will be x to the n minus 2, y to the 2. All right, and so that pattern will continue. At the very end, we would have a combination of n choose n, which is going to be 1, and then y to the n. So like this, notice, and this are the same value. And if we go back one term from the last one, now it's combination of n, choose n minus 1, and so on. So we can sort of combine this whole thing into a nice formula here with a sigma or summation notation. So remember, the summation notation is going to generate a lot of terms, right? It's going to start with 0, go up to n. That's going to be n plus 1 terms. Just like we know we're going to have, if we're raising it to the n power, then we know we have n plus 1 terms. And if we do a summation from 0 to n, our number of terms will be n plus 1. So the first time I put this in, r of 0 into this, it's n to the combination of n choose 0, which is what we have over here, x to the n minus 0, which would just be n, y to the r, which is also going to be 0. So we would get this term. When r is 1, this is going to be a combination of n choose 1, which is what we have in the next term. This will be x to the n minus 1, and then this will be y to the 1 power. So you can see how we would use the summation notation, and it would generate all of this. Okay, so let's use that idea to expand out this this binomial. Pause the video and then write that out, and then start it back up again. All right, so we're going to do, and I'm going to do every little step here. You want to start from the far to the left, hopefully, so you can fit it all, because this is going to have 9 terms, so that's a lot of writing. So write small and start to the left. Okay, so we're going to start with a combination of 8 choose 0, and then we know that's just x to the 8, and then plus combination of 8 choose 1, and then x to the 7. Y to the 1. We know my x values have exponents that are decreasing by 1. Y's are going to be increasing by 1. The coefficients are just found in the pattern that we saw up above. So the next term plus, this will be a combination of 8 choose 2, x to the 6, y to the 2, combination of 8 choose 3. And then, of course, we're going to go back and finish this, right? We can't leave it like this. We got to say what each of these things are. X to the 1 less, 5, and y to the 1 more, 3. And then we have a combination of 8 choose 4, x to the 4, y to the 4, combination of 8 choose 5, x to the 3, y to the 5. Notice too that the number down below and the exponent on the y are always the same. This number is the difference in the two numbers, right? So you can kind of get that without, now we're using the previous term, sort of using a recursive formula, using each previous term to get to this one, right? This was 4, so this is 3. This is 4, this is 5. But we could just use these numbers to help us kind of do it. And we'll see that in a minute. So a combination of 8 choose 6, x to the 2nd, y to the 6th, plus combination of 8 choose 7, x to the 1, y to the 7th, and lastly, combination of 8 choose 8, and then my x is to the 0, y is to the 8. And so now we want to simplify all this. We can't leave these combinations as they are. A combination of 8 choose 0. We're going to see in later section why we say 8 choose 0. So if you had 8 items and you had to choose none of them, how many ways could you do that? Well, that's just one way that you could do that. So that would be a 1, x to the 8. I'm gonna start down a little further because I need some. I'm gonna do some work in between, so I don't have to sort of rewrite it all again. So this is 1, or I could just say x to the 8. All right, the next one. How many ways can I choose 1 out of 8 items? Well, there's 8 ways to do that. So that's 8, x to the 7, y, or y to the 1 if you wanted. All right, how many ways can I choose 8 out of 2 from 8? That gets a little more complicated, so we need to do a little work on that one. So we'll do, remember this is going to be 8 factorial over 2 factorial, 6 factorial. So I'm going to use up my 6 factorial and give me 8 times 7 over 2. All right, and so that's 56 over 2, or 28. So 28x to the 6th y squared. Remember, too, that you can do this in your calculator as well. In your calculator, that is 8 NCR 2, and that gives us the same value. Okay, you should be able to do it by hand as well, but our calculator will do it as well. All right, and then this one, so this is 8 factorial over 3 factorial, 5 factorial, so that's 8 times 7 times 6 over 3 times 2. That simplifies down to 56. 56 x to the 5th y cubed. Okay? And again, we could get these numbers from Pascal's triangle, and in this case, because it's 8, we probably had that. If you look on the other page, you probably have that written out down to the 8th row. So you could just get these numbers from Pascal's triangle as well. All right, so now the next one. All right, so this is 8 factorial over 4 factorial, 4 factorial, so that's 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. That simplifies down to 70. So 70 x to the 4th, y to the 4th. And then the next one, this is 8 factorial over 5 factorial, 3 factorial. But remember, that's the same as this one. So we've already calculated that. I know that's 56. X to the 3rd, y to the 5th. This and this is going to be the same. So I know this one's going to be 28. X squared, y to the 6th. And then the second to last one then is going to be this one. These two are the same value. So I know this is 8 x y to the 7th. And finally, y to the 8th. Okay? All right, let's continue working with some of that. Let's go on to page 3 of our notes. And let's continue. So try example number 6. This one's got some fractions in it. It's a little bit more complicated. Pause the video and then try that, and then start up the video again, and I'll work through the problem with you. All right, so I'm going to write all this out. This one I'm going to put right up on top because I know it only has 5 terms. I should be able to fit it all. All right, so the first thing is going to be that this is a combination of 4 choose 0. And then the first term, which is m over 3 to the 4th power, right? And then the second term is going to be raised to the 0 power. All right, so then I'm going to add to this. I'm going to do a combination of 4 choose 1. It's now going to be the first term, m over 3 to the 3rd, and negative n to the 1. All right, I'm going to go back and finish simplifying all this in the next step, but I'm just going to continue. The next one is going to be a combination of 4 choose 2. M over 3 raised to the 1 less, or second power, negative n raised to the second power, plus a combination of 4 choose 3. M over 3 to the first power, and negative m to the third power. And then our final term, a combination of 4 choose 4. Oh, that shouldn't be written as a fraction. No fraction bar in there. 4 choose 4. And then times the m over 3 to the 0. So I'll just leave that off. Negative n. Sorry, I wrote an m in here. Negative n, and that's raised to the 4th power. All right, so let's go back and simplify these then. So 4 choose 0, well, that's just 1. And so that's going to be m to the 4th over 3 to the 4th, which is 81. All right, and now the next one is going to be negative, because this negative is not going away. It's being raised to an odd power, so it's going to be negative. We're going to have 4 choose 1 is just 4, And then we're also going to have a 27 on the bottom, so I could write that as a coefficient if I wanted. I could do 4 over 27, and then I could do m cubed n. I could write it like that. I could put the m and the n up on the top of the fraction as well, but I'll just leave it like that. The next one, this one's going to be positive because this negative is being raised to an even power. So a 4 choose 2. Well, let's see. 4 choose 2. That's 4 factorial over 2 factorial, 2 factorial. So that's 4 times 3 over 2, or 6. So we have 6 upstairs. On the bottom, we have 3 squared, which is 9. And then m squared, n squared. Okay? And then the next one is, well, we know these two are going to be the same, right, because of the symmetry. And so this will be 4 upstairs. Now, the 27 is not going to be the same. That's just going to be 4 over 3 this time, because the 3 is being raised to the first power. M, and then n cubed. Oh, that's being cubed, so this is a negative here in this time. All right, because that negative n is being raised to an odd power, therefore the term should have a negative. And then finally, the last term is being raised to an even, so I know it's going to be a plus. That's a 1, so plus n to the 4th. Okay, try the next one. Again, there's some fractions and some radicals in that. Could be a little tricky. Pause the video and then I'll work on the problem. And again, I'm just going to write right here because I know I only have 4 terms, so I should have enough space. Otherwise, if you write big, you might want to start down below. All right, so this is going to be a combination of 3 choose 0. And the first term is being raised to the second power. So 2 to the third power. 2 over y cubed to the third power. All right, and then for the next thing, I'm going to do 3 choose 1. The first term again, 2 over y cubed is being raised to 1 less, or the second power. And then the next term, negative 4 over the square root of y, that's being raised to the first power. Okay, the next term, we have 3 choose 2. And then the first term is now being raised 2 over this y cubed is being raised to the first power. And the second term, negative 4 over the square root of y is being raised to the second power. And then finally, we have 3 choose 3. And that's going to be negative 4. The first term is just being raised to the 0 power. I left that off. So now it's going to be negative 4 over the square root of y raised to the third power. All right, so now we just want to go back and simplify some of this. This one is just going to be a 1. So this is going to be 2 cubed, which is 8, over y to the 9th. All right, in this case, this negative is being raised to an odd power, the first power. So this is going to be a negative term. The combination of 3's choose 1 is just 3. Let's say 3, and then we're also going to get multiplied 3 by a 4, which is 12, and then 2 squared. So that looks like it's going to be 48. And then on the bottom, we're going to have, let's see, y to the, let's see, this will be a negative 1/2 power. So this looks like it'll be what, y to the 13 halves. All right, and then plus, next term is going to be plus because the negative is being squared. All right, and then let's see, this is going to be the same as this term, so that's going to give us a 3 times 2. And then times 16, that's going to be 96. So we have 96. And then on the bottom, this will just be y. That's y cubed, so that's y to the 4th. Okay, and then the last term is going to be negative because this negative here is being raised to the third power. So this will be, this is 1, so we can just ignore that. That's going to be a 1. So 4 to the third, that's 64. And then this here, this is y to the 1/2 cubed. This is going to be y to the 3/2 downstairs. I suppose we should probably get rid of these radicals. These essentially would be radicals, improper fractions in the denominator. So we would probably multiply top and bottom of this by a y to the 1/2, and also here y to the 1/2. So we can rewrite the first term y over 8 over y to the 9 minus multiply both top and bottom by y, so y to the 1/2, so 48 y to the 1/2 over y to the 7. And then this one stays the same, 96 over y to the 4th. Again, multiply top and bottom of y to the 1/2 here. This gives us 64 y to the 1/2 over y squared. Okay, so that's kind of your best and final answer. Okay, so you can see we've used Pascal's, we use the binomial theorem sort of to generate these things. But ultimately, in something like this, I probably would just go back to Pascal's triangle. I probably would have just looked at this and said, oh, well, I know my coefficients are 1, 3, 3, 1. So with something as small as 3, then it's probably easy enough just to go back and do this the same way we did on the front of this page, on page 1 of section 11.4, where we just used Pascal's triangle. Remember, what row do we use? We use the row with the first number that's not a 1, and that tells us that the exponent on the binomial. So I'm going to use this row when it was cubed, right? When this row was, I used a 4 up here, so I would use this row. Also, think about it. If it's to the 4th power up here, I know I have 5 terms. Which row has 5 terms? Well, this one. 1, 2, 3, 4, 5 terms. So that kind of tells you what row you have to be in anyway, because you know how many terms there are. All right, so so it's easy enough when the exponent is rather small to just use Pascal's triangle and what we learned on the front of this page, on page 1 of these notes. But sometimes the binomial theorem is useful when the exponent is rather large. Say, you know, if I had it to the 21st power, we wouldn't really want to use Pascal's triangle. Or if I'm looking for just a particular term, and we're going to get to an example of that in a second. Rather than writing out the whole expansion, I just want the 5th term of the expansion. Then sort of going and using Pascal's triangle, I mean using binomial theorem rather than Pascal's triangle probably makes more sense. All right, so we use the binomial theorem to expand a binomial, but what if we just want one particular term? All right, so that's what we're going to get into now. So if I want to expand this out, I know I'm going to use the summation starting with an r value of 0 going up to n. Of course, that gives me how many terms? That will give me n plus 1 terms. So remember that we're starting our counting with 0. So if we look at how we expand this, like let's say expand this thing. So for the first term, if I wanted to find the first term and the first term only, I mean, certainly I could expand everything out, but if I wanted just the first term, what would the r value be for the first term? So look at our index here. 0 would be the first value of r for the first term. So if I wanted to find the first term, I could put a 0 in for r. If I was asking you to find the second term, well, I increase my r value by 1, and so r would be 1, and then of course 2 and 3 and 4 and 5. So the whole idea is the r value that you're going to use to find a particular term is always 1 less than the term you're looking for. So if I'm looking for the 5th term, I use the binomial theorem, but I know that I'm looking for an r value of 4 because we start our counting at 0. Okay, so this is how we're going to find a particular term. So in other words, in order to find the 3rd term, I first found the 1st, the 2nd, the 3rd, right? But we're not going to do that process. We want to just jump and find the particular term. So we want to find the 4th term of the expansion of 2c minus d raised to the 12th power. Well, now that's great, but the thing is, I don't know what the Pascal's triangle is for 12. We never make a triangle that big. So, and it's a little tedious, quite honestly. So we'll use, in that case, makes more sense to use the binomial theorem. So first of all, let's write down what our r and what our n are. So the n is always the exponent. So in other words, if you look at the formula up here, right, n is always the exponent. R is the value I'm going to plug in to find my particular term, but my R value is always one less. So if I'm looking for the fourth term, my R value should be 3. So R is equal to 3, N is equal to 12, and simply plug that in to the binomial theorem up here. All right, so my X in this case is 2C, my Y is negative D. All right, so I'm looking for the fourth term. So I'm not going to do the summation because the summation is what gives us the whole expansion. So it's not really the expansion. What I want to do is do 12, choose 3, right? Because that's what my R value will be for the fourth term. So I'm going to use 12, choose 3, and then I'm going to do 2C, I put the whole thing in parentheses, raised to the n minus r, or 12, I'm going to just write it out here as 12 minus 3 to start with, and then negative d, then that's raised to simply the r power. So that's going to be 3. So notice too, when I add these two exponents up, it gives me 12 as well. All right, so I want to sort of simplify that a little bit. All right, so this is, remember, 12 factorial over 3 factorial, 9 factorial. So I'll be left with a 12 times 11 times 10, and then the 9 factorial cancels with the 9 factorial on the bottom. And then on the bottom, I still have my 3 times 2 times 1 if I want, okay? And then this becomes 2 to the 9th, C to the 9th, and then negative D to the 3rd. Okay. So I can think about this negative being raised to an odd power. So that negative is going out in front as part of my coefficient. So is this 2 to the 9. It's also going out with whatever's left here. So when I simplify this and I multiply 2 to the 9th and I have my negative, my answer is going to end up being negative. Well, let's bring that out first. And then this all simplifies down to 220. And then 2 to the 9th, that's 512. And then we have C to the 9th, D to the 3rd. So finally, simplifying all of that down, we get negative 112,640 C to the 9th, D to the 3rd. So that is our final answer. We know it has to be negative because this negative is being raised to the odd power. So don't lose your negative. Try the last one, number 10, and then pause the video, and then I'll do the work here. Okay, so what would the R be? We're looking for the 7th term, so our R value will be 1 less than that 6. Our N, in this case, again, 10, same as the exponent. All right, so this will be, the 7th term will be a combination of 10 choose 6. Then it's going to be the A, which is the first term, A, raised to the difference in these, which is 4, and then 2b, all raised to the 6th power. All right, it's always the R value that's there. All right, and so now we just need to simplify this a little bit. Remember, this is 10 factorial over 6 factorial, 4 factorial. So I'm going to cancel the 6 factorial and leave me with a 10, 9, 8, 7. Over, and then the difference was 4, so 4 times 3 times 2 times 1 if you want. All right, and then this will be also, let's put the number out in front, so that'll be times 2 to the 6th, and then A to the 4th, b to the 6th. All right, so now we just got to simplify all this. When we cancel a couple of these things here, we end up with 210. 2 to the 6th, that's just 64. In this case, there's no negatives in here, so there's no way that this would be negative. A to the 4th, b to the 6th. And then when we simplify this together, we multiply that, we get 13,440, a to the 4th, b to the 6th. All right, so the binomial theorem here then is useful when we are trying to find a particular term or trying to maybe expand something that has a really high exponent. Remember, the Pascal's triangle really only goes down to about 8. I mean, you could make this as big as you want, but it gets pretty cumbersome once you end up going beyond 8. So if the expansion is asking you to raise it to the binomial raised to the 8th power or lower, then probably Pascal's triangle makes the most sense. If it's something larger than that, then you probably want to use the binomial theorem. And in particular, you want to use the binomial theorem if they're asking you just for a particular term. So, I mean, you know, to get the 7th term here in this last example, you would have to find the 1st, the 6th, the 2nd, the 3rd, the 4th, the 5th, to, you know, find them all using Pascal's triangle, which is cumbersome. Here, we just use the idea of the Pascal's binomial theorem then to find a particular term. The key is finding the right R value. Remember, the R value is always one less than the term that you're looking for, because our binomial theorem always starts with our counting index, our summation index, or index of summation, always at 0. Also remember too that this exponent is the same as the R. This exponent is the difference in the n and the r. That always happens. Okay, so you have some homework that's due next class period, next time we meet. Okay. Remember, if you have any questions, come see me at lunch.